Are you ready for video number 4 in our journey into what an atom is and atomic structure? Yeah, I hope so. That's why you're watching this video. Or you just have nothing better to do, or you're just innately curious into chemistry and how the world works, right? Some of you watching this, maybe you're not in college, you don't care about it, you just have this love to learn. That's what I do chemistry. That's what I majored in. Originally, it was chemical engineering, but found out I wasn't really a good engineer, so I went straight chemistry. And I was interested in music. I was working on a music minor, but found out I really didn't like analyzing music. I just liked to sing. I just wanted to perform. So I ended up going straight as a chemistry major. And then when I went to grad school, I specialized in certain because chemistry is really broad. So you specialize when you go to a master's or a PhD. But I learn a lot of stuff that's not when I'm at home. I read a lot of history and economics, and I just love psychology. The amount of learning I've done, would that be equivalent to a degree? I don't know. But I have a lot of friends who, they just love science. They didn't officially study it, but they're exceedingly smart when it comes to science, and they can have a good one-on-one conversation with me. One of you might be watching this right now. My sushi friend or price man, hey, rock and roll. Here we go. What if we change the number of neutrons? Well, how does that affect the atom? So if we have multiple atoms of an element that have the exact same number of protons, their identity is the same. It's the same element, right? Same number of protons. If they have the same number of electrons, they'll have identical chemistry, right? Because the number of electrons, we'll find out later, the electronic structure determines the chemistry. But what if they had different number of neutrons? Because you can change the number of neutrons and not change the chemistry of the atom, which is determined by the electrons, and not change the identity, because that's the number of protons. So it really doesn't impact it much other than the mass, right? If you add an extra neutron, it gets heavier. So you can have different atoms of an element that are exactly the same, other than one is heavier than the other. It has a higher mass. Those are called isotopes. Really, really key. We probably won't work on these for the rest of the semester after this particular section. But when you get into maybe medicinal chemistry, you do a lot of isotope work, radioactive tracers, diagnostics, cures. Atmospheric chemistry, I did some atmospheric chemistry, so you can use isotope tracers in the atmosphere. It's really fascinating when you've all heard of carbon-14 dating, things like that. They use these isotope ratios for geological dating and whatnot. Just fascinating applications of isotopes, which we unfortunately don't have time to get into. I'm just introducing you to it. But, there's some really cool careers made out of isotope chemistry. Here we go. John Dalton, remember John Dalton's atomic theory? That was early 1800s, way before they discovered subatomic particles. He did not know, couldn't even conceive of the idea of neutrons and electrons and protons. Remember, he postulated that all atoms of an element are identical. Well, that was a valid postulate back in this time, but it turns out that wasn't quite technically correct. Right? He they had the same number of protons, same number of electrons, but he had no idea what neutrons were, and that you could have atoms that were different in a specific element just because they have different numbers of neutrons. This gets fun. All right, next board. When we are talking about isotopes, we have to be very specific in our language. All right? Move that over a little bit. Because you can have different number of neutrons. So figuring out the number of protons is pretty easy from the atomic number. We'll be able to get that straight from the periodic table. Number of electrons should be easy because those equal the number of protons if it's a neutral atom, right, or neutral isotope. If it's not neutral, we just used what we learned from ions, right? If it's positively charged, that means it lost some electrons. If it's negatively charged, it means it gained electrons. So if it's a -3 isotope, it has 3 more electrons than protons. If it's a +2 isotope, it'll have 2 less electrons than protons. So you can figure the number of electrons out from the charge of the ion and from the atomic number, which you get from the periodic table or it's provided to you. But the number of neutrons, that's a harder one to figure out. Because remember, that can vary, right? It gives you different types of isotopes. And each element has a certain number of isotopes. Some of them might have 3 different types of isotopes. So 3 atoms with different numbers of neutrons. Some might have 7. Some might have 2. So let's review some of the notations we've used and then look at some new ones. So remember Z, that's the atomic number, the number of protons in the nucleus that gives the identity to that particular, what atom or isotope is that, from what element, right? Now, here's a new one, mass number. This creates a little confusion with atomic mass. This is different than the atomic mass. Mass number is a number of particles. We call it capital A. It's not what I would have called it, but we call it capital A. That is the number of protons plus the number of neutrons. And remember, protons and neutrons are the only particles, subatomic particles, inside the nucleus. So those are called nucleons, particles in the nucleus, your protons and neutrons. So if you add all the protons and neutrons together, you get the total number of nucleons. So really, the mass number is the number of particles in the nucleus or the number of nucleons, right? Protons plus neutrons. So the only way to figure out the number of neutrons in a specific isotope, if it's not provided, is to know the mass number. So when we identify isotopes, there's an isotopic notation we're going to use. You have to give someone the mass number, otherwise you'll never be able to figure out how many neutrons are in that particular atom of atom of the isotope of that particular element. So using this, I can create an equation, right? If A, the mass number, is the number of protons plus neutrons, then the number of neutrons will be equal to the mass number, which should be provided to you, minus the number of protons, which you can figure out from the atomic number, which you can get from the periodic table. We'll show you. So number of neutrons will be A minus Z. Just take the bigger one minus the smaller one. You can't have a negative number of neutrons. That makes no sense. None whatsoever. How can you have a negative number of subatomic particles? That's just weird. All right, let's look at isotopic notation. Most students just love this stuff on exams once you get it. All right, here's our 2 types of isotopic notation. Oh, I dropped something. Running over it with my chair. We've got the standard notation, which I think can be fairly redundant. And then the more commonly used hyphenated notation, I call it the shortcut or the long form, short form. Let's look at the standard notation generically, nothing specific at this point. Because you need some extra information to figure out the number of neutrons. You can't look at the periodic table and go, oh, there's the number of neutrons. You can't do it. You have to be given the mass number A, right? So let's just call X the element symbol, right? Whether it just has, 1 letter like nitrogen, capital N, or oxygen, capital O, or 2 like manganese, capital M, lowercase n, or tin, capital case S, lowercase n. Remember, never do 2 capital letters in an element symbol. It's always, the first one's always capitalized. The second one, if there is one, is always lowercase. So use X as the element symbol. If it has a charge, right? Most isotopes are probably going to be neutral atoms, so you don't need to put anything there, right? So if there's nothing there in the upper right corner, you think of it as 4 quadrants, right? You got the upper left, upper right, lower left, lower right. Those all have specific information that goes there. So if there's nothing there in the upper right corner, then you're assuming it's a neutral atom. If there's a charge there, like a plus sign, like a positive 2, or if it's just a plus, it'd be positive 1, or maybe a 3 minus or something. Obviously, that means it's an ion, and you've altered the number of electrons. So watch out for that. The lower left is signified for the atomic number, or the number of protons, which we can get that straight from the periodic table. So if you look at any periodic table, that number right up on top there, right, there's 9 for fluorine, 10 for neon, 8 for oxygen. That's your atomic number. That gives the identity, right? So you can always just look on the periodic table and know what Z is. You can just look at it. Or if you know what that number is, you can look at a periodic table and tell me what element it is, so you can figure out unknown identities from that. The upper left quadrant is for the mass number, which is the number of nucleons, number of protons plus neutrons, right? So if you take A minus Z, right, the bigger number minus the smaller number, that gives you the number of neutrons, the number of neutrons. So that's the long form. And the reason the short form exists, because if you agree with me, this is redundant. If you have a periodic table with you, which you should. I highly recommend getting a wallet-sized one. Put it in your wallet, back pocket, maybe a nice tattoo with a periodic table on your arm. I should think of that. I should ask my family what they think about me getting a gigantic, or maybe a big giant tattoo with a periodic table on my back, which wouldn't do me any good because then I couldn't look at it. That makes no sense. If you have the periodic table and you know the element, you automatically know how many protons it has, right? So really you don't need the value of Z right there. It seems redundant. Now, if you don't have a periodic table, that helps. But if you're a chemist, you have a periodic table with you, so you don't need that. And that's why the hyphenated form is here. So in the hyphenated form, you have to have the element symbol, which then gives you the number of protons, and you can figure out the number of electrons from that. And then we use a hyphen. That's not a subtract. It's not X minus A. It's X hyphen A, hyphenated form. So you do the element symbol with a hyphen and then the mass number, which you need to get the number of neutrons. So given either one of these notations, you could tell me the number of each type of subatomic particle. How many protons, how many neutrons, and how many electrons, easily. If that particular isotope is charged, you would put that, if it's an anion, cation or anion, you'd put the charge on the upper right of the element symbol there. So let's practice some of these. Take a look at them in general. I got a little room on the bottom here. A simple one would be like carbon 4. I think you've all heard of carbon 14 dating. Turns out carbon has several isotopes. Carbon 12. That's the way we talk about notation. You say the element and then the mass number. So carbon with a mass number of 12, carbon 12, if you look into nuclear chemistry, it's one of the by far the most common isotope of carbon, and it's very stable. Carbon 13 is another one, and carbon 14. There's not a lot of carbon 14. If I had 100 atoms of carbon, for example, probably, 95 or so might be carbon 12. Just 1 or 2 might be carbon 14. I don't know the exact numbers off the top of my head, but there's very few of them. And it turns out they're actually unstable, so they undergo radioactive decay. And you can utilize that unstable nature of the nucleus to do a lot of cool things with it. We're not going to get into radiocarbon dating and whatnot, but it's fascinating stuff. So if I wanted to do the symbols for carbon 14 over here, now if you look on the periodic table, find carbon, that has a number 6 there, right? So that has a Z of 6. So if I'm going to write it, I would write carbon. I would put the 6 down there because that's the number of protons. It's carbon 12. So the mass number would be 12. So you can see 12 minus 6 would be 6 neutrons. So it would have 6 protons. 12 minus 6 are 6 neutrons. And if it's neutral, I put nothing there, it would also have 6 electrons. Oh, it's evil. We would draw it like that. If I was doing the shortcut, I would just draw the element symbol for carbon. Don't need the atomic number. I draw a hyphen. Oh, I was going to do carbon 14, wasn't I? Let's erase that and put a 14. It doesn't matter. Now, the only difference is we had carbon 12 there earlier, so 12 minus 6 would be 6 neutrons. Now we have 14 minus 6, would be 8 neutrons. And that's neutral. So both of those are acceptable. So if I ask for isotopic notation, I don't specify which form, I'll take either one. Doesn't matter to me. But by far, most people use that one. And that's the language, carbon 14. Or like I did before, I said carbon 14, and I put carbon 12 up there. Let's do another board. I'll throw a bunch of different examples at you and show you how we can, work from a notation to the number of subatomic particles. Or if I give you the number of subatomic particles, you can give me the notation. You can identify unknown elements, right? Let's say I don't give you the element, it's an unknown, but I give you the number of neutrons and the mass number. Well, you can calculate the number of protons, look on the periodic table, and figure out the identity of that unknown. So a lot of cool things you can do with it. So let's do, 2, 3, 4 examples, and I'll try to hit you out, throw a fastball at you, a curveball, and a changeup or something. Let's see what we can do. Whew, almost ran out of juice on my laptop there. That would have been bad. Right in the middle of a video. Bloop! Computer dies. You had to do the whole thing all over again. Here's a type of example you might see on a quiz or exam. So pay attention. Here we go. An unknown isotope, unknown, has a mass number of 226. So what does that mean? 226 nucleons, or the number of protons plus neutrons is 226, right? And it contains 138 neutrons. All right. Well, that means we should be able to figure out the number of protons quite readily. I should probably tell you how many electrons it has as well, right? Because we don't know. I should note that this is neutral. An unknown, let's put neutral right here. Otherwise, there's no way you'd be able to figure out the number of electrons. So an unknown neutral isotope, so number of electrons equals number of protons, has a mass number of 226 and contains 138 neutrons. What element is it? All right. Well, remember, the mass number, by definition, is the number of nucleons, or protons plus neutrons. Do we know the mass number? Yes. Do we know the number of protons? We don't. Do we know the number of neutrons? Yes. So we can solve for the number of protons from that. And of course, once you know the number of protons, you look on your trusty periodic table to find what element it is. And then it doesn't say to write the notation, but we might as well. So let's look this up. So the number of protons will be the mass number minus the number of neutrons. So what's our mass number? 226. Number of neutrons, 138. These are all exact values. There's no uncertainty. These are counting number of particles, right? You either have 8 protons or you're not. It's not 8 plus or minus 2. These are exact numbers, so you don't have to worry about uncertainty with this. So let's grab your calculator, take 226 minus 138. Let me pop my knee there. Oh, injuries that just go with you your whole life. Lots of fun. So I get 88. Protons. So let me grab my periodic table. Oh, man. I cannot read anything here. All right, let's find number 88. Where I got C. Is that it right there? That 88 right there? So is that radium? Looks like radium, which would make sense. Radium, radioactive. Radioactive. And that's all the problem really asked for. But we might as well do the notation for it. Since we're here, we don't have anything better to do. So let's write the symbol. Radium. And its atomic number is 88. Its mass number was 226. And that was neutral, right? Or we could do the hyphenated form. Do the radium with the 226. And that would be the terminology in that field. If you were a specialist in isotopic science, you would call that radium-226, that specific atom of that element, radium. Sweet, let's do another. Not too bad when you know what you're doing. It's very easy to do. And this is not an equation. It's not really an equation I'm going to give you. It's a definition I would expect you to know. Mass number is number of protons plus neutrons. And with that, you can do anything you want. Let's do another one. Another type of problem you will most likely run into on a quiz or exam. So, what element is that? If you don't know, you got to waste 5 minutes looking it up on the periodic table. That's thallium, I believe. So thallium-203, that's that hyphenated or short form notation. Thallium-203, 203, that's the mass number, right? Number of protons plus neutrons. Just extraneous information used in heart muscle research. So much use in medicinal chemistry. How many of each subatomic particle are there? Now, that's neutral, right? There's no charge written on there, so we know the number of protons must equal the number of electrons. So the first thing we have to do is look up thallium and find its atomic number. So let's look up the number of protons, number of electrons, right? The number, how many of each, not the total, how many of each are there? So we need to do the breakdown of the different types of subatomic particles. So grab your periodic table, see if you can find thallium. Where's thallium? Thallium, is that thallium right there? TL? Yep, thallium. That's 81, baby. So we've got 81 protons. This is neutral, so the number of protons must equal the number of electrons. Righto, daddy-o? So that's neutral. You don't have to write this. That's just something, so if you're looking back going, how come you got the same number? Because it's neutral. There's no charge on there. Maybe we should do an example with a charge. Oh, maybe next. Number of neutrons. You can't look at the periodic table and find the number of neutrons, only the number of protons. So we need the mass number to do that. Let's figure this out. So we know that the mass number is number of nucleons, or protons plus neutrons. So number of neutrons is the mass number minus the atomic number, correct? So what's the mass number? 203. What's our atomic number? 81. These are exact numbers. So what's 203 minus 81? Doop, 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 doop. Plug it in. You can probably do that in your head. I don't know if I could. What is that going to be? 122-ish? Double check me. So if that's the case, there would be 122. So 120, 203. Yeah, that looks about right. So if you add these together, you should get 203, those two. So that particular isotope of thallium has 81 protons, that's its identity, 81 electrons, defines its chemistry, and 122 neutrons, which helps you figure out its mass. Now, we haven't covered atomic mass yet. Remember, mass number is not atomic mass. They're close. Because remember, almost all the mass of an atom is in the nucleus, the protons and neutrons. It takes like 1,800 electrons, about 1,800 electrons to equal the mass of like one proton or one neutron. So literally, almost the entire mass of an atom is located in the nucleus, which is the number of nucleons, which is the mass number. So yes, the mass number, atomic mass are very close, but they are not the same thing. The mass number is the number of particles in the nucleus. The atomic mass is the mass of that particular, you could do an isotopic mass, the mass of that specific isotope. But if we do the mass of an atom, remember atoms contain lots of different isotopes. So we're going to have to use some statistics and do a statistical average over all the different isotopes to figure out the statistical average mass of a particular atom. That becomes a problem. That will be a video in and of itself. But remember, mass number, atomic mass, not the same thing, close, but not the same thing. All right, let's do one that has an isotope this time, a charged isotope. Last one, I promise. Pretty easy stuff, right? Go through the homework. You'll be well set for the quizzes and stuff. All right, write the isotopic notation for an isotope of iron that has 33 neutrons and 31 electrons. Oh, all right. So I gave you neutrons and electrons. I didn't give you the number of protons, but you can find that on here. And once you have all the subatomic particles, you're good to go. So let's go ahead and list those out. All right, let's do number of protons, number of electrons, number of neutrons. So gave me neutrons. So this is a different type. I gave you 3 examples, which are really about the only 3 ways I can kind of twist these problems on you for isotopes. I gave you the number of electrons. Let's look up, we know it's iron, so let's look up iron on our trusty periodic table. Iron, right there, my friends. Do you see the 26? So iron has 26 protons. So now we're rocking. We can figure this out. Let's get our mass number. Remember, we need the mass number. So mass number is the number of protons plus the number of neutrons. So protons is 26, right? Neutrons is 33. Those are exact numbers. What do we get? 59. So that's our mass number. Now we have everything we need, and let's just lump it in. I didn't specify whether it was the standard notation or the hyphenated notation, so you can do one or the other, or both. You know, if you got extra time on your test. Right. Here we go. We know it's iron. Iron, lower left would be the atomic number, right? So that'll be 26 there if I'm doing the standard notation. Mass number is 59. 59. Now, is it neutral? Are the number of protons and electrons the same? They do not look the same to me, right? At all. So if they're not, so we have more electrons than protons here. More electrons than protons. 31 electrons. So that number, I'm going to have to change that number, because iron is not going to be a negative charge. So let me change this real quick. I'm going to change this 31 to a 24. 31 to a 24. Let's do that. This will make more sense. Right? Otherwise, we end up with like a -4 charge or something like that. So let's try it this time. So on your notes, make it a little erase mark. Erase the 31, put a 24 there. It happens. So now we have more protons than electrons, correct? So 26 minus 24 is 2, so that's going to give us a +2 charge there. So that would be our standard notation, which we don't need. We have iron, so we don't really need the 26. So let's do the hyphenated notation, where you draw the iron. If it has a charge, which it does, put the charge on there. Give me the hyphen, and then give me the mass number, which is 59. So standard notation, hyphenated notation, I don't care which one you give me there. So yeah, gave you the wrong number of electrons there. That wouldn't have made any sense. So this should make sense. Now, if you have more electrons than protons, you're going to have a negative charge there, right? If you have more protons than electrons, you'll have a positive charge there. Easily fixable. So that's isotopes for you. Go with the data provided, and you can rock with this, guys.